Okay, in this lecture we are going to have a review with regard to memory management. And now I'm going to discuss whatever we had discussed in the class with regard to memory management so that we can continue with the new topic, because it's been a long time since we had the class. So I thought maybe first we have a brief review with regard to all the topics that we discussed in memory management. See, we said that memory here refers to main memory. So managing main memory implies managing the user space. If you remember and recollect, if I say this is my memory, main memory, it is generally divided into two parts. One part meant for storing operating system, that is called system area, and the other area is called user area. User area will store user applications or user submitted programs. In case if it is uniprogrammed operating system, then this user area will be capable to store only one program, and if it is a multi-programmed operating system, then this user area is meant for storing several programs. So maybe perhaps I can store program P1 here, P2 here, P3 here, and so on. So many programs can be stored, and this aspect of storing multiple programs is generally called multi-programming. So in a typical multi-programmed operating system environment, managing main memory implies managing this user space. Now, what are the issues that are to be considered in the management of this user space? The important issues include allocation. That means which portion of memory are we supposed to place the program in. Then basically protection. Essentially, we said that this area of memory where the user program is stored is called program address space. So when it is loaded in this address space, it is supposed to confine its execution within this address space. It cannot access the other program address space. It cannot interfere with operating system area. So this aspect is called protection. If you remember and recollect, I have just gave you a diagram. You can refer the notes. Protection can simply be done by using some registers like base register, limit register. Base register will store the starting address of the user area or user address space of that program, and the limit will contain the size of the partition, so that whenever the program generate any address, we will check whether this is within this base and limit or not. This is called protection. So protection is a very important function of memory management for multi-programmed operating system. Then the next issue is nothing but free space management. That means how to keep track of free space. There are algorithms. We need to discuss this topic at later point of time. And then maybe we can say address translation. This aspect also I had a brief discussion in the class during the lectures that we had. Address translation means the address generated by the user program when it runs on CPU is generally called the logical address, whereas the address that is needed to access memory is called physical address. So essentially we need to have a mechanism where we should be able to convert logical address into physical address. So how is that going to be done? That we have to look into different or by means of different memory management techniques. So these are the important issues that we need to address upon the memory management technique. The first important technique that I discussed in the class, if you remember and recollect, is called swapping technique. So I gave a detailed note. I have explained to you in the class. I'm just trying to review here, summarize here, so that you can try to memorize, conceptualize it, memorize it. In swapping technique, we maintain a backing store. So okay. So here, if I have memory, okay, and we will have backing store. What is backing store? Backing store will be nothing but a disk. So all user programs will be there on the backing store, and here we may have the operating system. And in the user space, we can have different programs, for example. And I told, if you remember, the operating system will maintain a ready queue, maybe there in memory or maybe there in the backing store, which will contain all the programs which can be executed. So what happens is, whenever the operating system scheduler, CPU scheduler, decide to schedule some program, if the program is already in memory, then it starts executing on CPU, and if it is not present in memory, then and if I don't have enough space present in memory, then we'll swap out one program and swap in the desired program into main memory. This process is called swapping. So I would advise, please have a review, look at the notes and try to see the notes with regard to swapping, what are the issues. I have just given a brief introduction to brief revision, I would say rather. Now the actual memory management techniques that we had a discussion in the class was pertaining to the classification. So how are memory management techniques classified? If you remember and recollect, I said that memory management techniques are classified into two types. What are the two types? Let's discuss them. Okay, the classification, basic classification of memory management techniques falls into two categories. One is called contiguous and the other is called non-contiguous. You can see all these whatever I am discussing, and in fact the discussion, I would say, is a review rather. Okay, I gave a detailed note of all these in the notes. You can check it. And just because it's been a long time, as I said, so therefore I thought before I start with the next topic, you should have a clarity of understanding with regard to the new topic. So this is a brief discussion with regard to whatever we discussed so far in memory management. Now what happens in contiguous allocation? In contiguous allocation, we will also call it as centralized allocation. Centralized means the whole program as a unit will be at one place. Say for example, this is the memory. Okay, so what happens is if I have a program P1 of size 100 KB, then the whole program P1 will be at one place. It's not that the program will be divided into different parts and different parts of the program are stored at different places. So the whole program will be at one place. Whereas non-contiguous allocation will follow a decentralized approach, decentralized or distributed approach. So what is going to happen in decentralized approach? In the case of decentralized approach, if you consider this as the memory, okay, so the whole program may not be at one place. I'm saying may not be, I'm not saying will be, okay, may not be. Maybe if I have a program of 100 KB, we may divide it into several parts, and different parts of the program may be stored at different places. Like one part of the program may be placed here, another part of the program may be placed here, still another part of the program. So if I divide this into 3 units, for example, 30K, 30K, and the other will be 40K. So maybe one part here, another part here. Okay, this is 130K, there is another 30K, and this is another 30K. This is called non-contiguous, means the whole program is not at one place. It is distributed in different areas of memory. That is what is called non-contiguous allocation. Followed? So what is going to happen in non-contiguous? After seeing the classification, I would also first give you a review with regard to the contiguous allocation. Okay, contiguous allocation. The major important technique that we discussed in contiguous allocation, if you remember, basically was like partitions. All right, partitions. If you remember, I discussed in the class, I recommend you that you refer the notes and try to see this discussion that we made in the class so that you can recollect and we can proceed with the new topic. Partitions, if you remember, I said are classified into fixed and variable. Fixed partitions and variable partitions. Fixed partitions is also called MFT, multi-programming with fixed tasks, and this is also called MVT, multi-programming with variable tasks, variable partitions. All right. So in fixed partitions, I will quickly review what we have discussed in the class so that you can be in a position to recollect it. All right. So what is going to happen in fixed partitions? I will just review tab, slightly slide it down. Okay, right. So let's say fixed partitions. I hope you are able to see the handwriting, understand the handwriting also. So what is going to happen in fixed partitions? So I'll quickly review. Suppose if you say this is the user space or user area of memory, it will be divided into fixed number of partitions. All right, each one is called one partition. Partitions may be of different size, like for example, this may be 50 KB, this may be 130 KB, okay, this may be 250 KB, 250 KB, and this is another 30 KB. So when I say that this partition is of size 50K, it can be able to store any program up to 50 KB. Okay, and the other one is 130K, so therefore it will be able to store a program of size 130 KB. This can store a program up to a capacity of 250K and so on. So the important issue here is allocation. Allocation means when a new program comes, which partition are we going to accommodate it? There may be many eligible partitions. Like if you remember, I said if I get a new program of size 25K, if you remember, if you believe that all these partitions are free, maybe we can accommodate 225K here or here or here or here. All are eligible. So which partition are we going to place it? So for that we said we have techniques like, for example, first fit, or maybe we can say best fit. I hope you are able to recollect. Okay, worst fit. What is going to happen in first fit? So the partition, we start searching from the first partition to find out which is whether it is big enough to accommodate the process or not. If it is big enough, then we place it. If it is not, then we go for next free partition, that is first fit. So therefore we say first free big enough. Now in the case of best fit allocation, we say the smallest free big enough partition, and the worst fit means largest free partitions. Hope you remember and recollect what I discussed in the class. Okay, so that was allocation. Second, protection. If you remember and recollect, I said in the class that for protection we use base and limit registers. I have explained to you by means of the diagram. If you remember and recollect, you can review it from the notes. Now coming to performance of this, we said this suffers from internal fragmentation. Remember, internal fragmentation we defined in the class. Internal fragmentation means the amount of memory that goes waste after placing the process within the partition. Like what I'm saying, for example, if you just climb up, if I have a program of size 25K to be accommodated, okay, 25K I want to place it, maybe I can place in 30K, 250K, 130 and 50. Suppose if I place in 50K, so size of the partition is 50K and the program needs only 25K of memory. So the amount of memory which is left over within the partition, like after placing 25K, I get 25K free. Now this cannot be used for storing any other program, because one partition can hold only one program, and one program cannot be accommodated in more than one partition, 1:1. So the leftover memory within that is called internal. Why internal? Because it is within the partition. So therefore that is internal fragmentation. So therefore it may suffer from internal fragmentation. So hereafter we'll write internal fragmentation as IF. Now there is no provision of external fragmentation, I discussed in the class if you remember. And fixed partition will also have what do you say, the drawback of limited degree of multi-programming. I cannot have more than 4 partitions are there. I cannot have more than 4 programs at a time present in memory. So that is another limitation of fixed partitions. And then the maximum process size, the moment I am creating a partition of size 250K, so that means I cannot have more program of size more than 250K. So that is another limitation that we can have with fixed partition. So how are we going to overcome those limitations? That can be overcome by using variable partitions. Remember, variable partitions. So what is going to happen in variable partitions? In variable partitions we follow a dynamic approach of partitioning. Dynamic. So what is dynamic approach in partitioning? The user space will not be divided into fixed number of partitions, but the partitions get created as and when we start getting the programs. So if I get a program of size 25K, exactly I will create one partition of size 25K and place the process there. So say for example, if this is my user space, and if I want to put one program of size 25K, so I'll put P1 25K. Then P2 comes of size 70K. So one partition will be created of size 70K, and like that it goes. So essentially there is no internal fragmentation here. So therefore there is no internal fragmentation. We said this will have external fragmentation. External fragmentation because between the partitions I can have free space, and that may go waste. Remember, I gave the definition of external fragmentation in the class in the notes. You can refer it and check it. So okay, so that is external fragmentation. And then it has flexible degree of multi-programming. Flexible degree of multi-programming. Multi-programming is flexible. And maximum process size runnable is also good. So the only drawback that this scheme suffers is from external fragmentation. So the problem of external fragmentation can be overcome by using an approach called compaction, I said. Okay, compaction. or the other approach is called non-contiguous. What is compaction? Please refer the notes and try to recollect. So in compaction, we push all the programs at one end of memory and then we create one big free hole at the other end of memory. That is called compaction. And the sorry, next approach that we use generally for solving the problem of external fragmentation, we said, is non-contiguous allocation. Non-contiguous allocation, broadly there are two techniques we said. One is segmentation and the other is paging. Okay, so I'll just quickly review, okay, for your convenience. You can, however, are advised to refer the notes in order to see the details of this, because repeatedly I'm saying this is only a review lecture so that we can be in a position to continue our discussion. So in segmentation, generally we first introduce the concept for both segmentation and paging. We introduce the concept of something called logical address space, virtual address space, and physical address space. Okay. Kindly see these definitions I gave in the class. What is logical address space? I explained to you also, and what is physical address space. To access the logical address space, we generate the logical address or use the logical address or virtual address, and to access the physical address space, we use the physical address. We said that the program running on CPU always generate logical or virtual address. Okay, logical or virtual address, but the address which is needed to access main memory for our program instructions and data is called physical address. So we need to convert this, and the unit that does this conversion we said is called memory management unit. So it takes logical address as input and gives the corresponding physical address as the output. So paging has its own approach of implementing this, and segmentation has its own approach of implementing this. So first I would advise everybody to please review segmentation, which I presented as a technique in the class. So we said, if you remember quickly, I'm summarizing. If this is my logical or virtual address space, this will be divided into units called segments. Segments may represent functions like main, function f, function g, function square root, or something like that. These segments will be kept in main memory at maybe different locations. All right. Maybe I can store one segment here, segment 0, segment 2, and so on. This is my physical address space. So program will generate the logical address, which will have two parts. I hope you can see the notes for the detailed diagram. I'm just only putting it in a summarized way. This will be divided into segment number and offset. Every segment is given a number: segment 0, segment 1, segment 2, segment 3. So this segment number may refer to any of these, and offset means which word of the segment you want to refer. So therefore, using this translation scheme, we can convert the logical address to physical address by means of a table called segment table. Remember, segment table will have base address of the segment, say segment X, say base, and the limit of it or the size of it. Okay. So using this segment table, we can convert the logical address to physical address. So the logical address having segment number and the offset D will be converted into the physical address, which is nothing but base plus offset. Remember that? I discussed some problems also, if you remember and recollect. So I strictly advise everybody to refer the notes for the detailed discussion of segmentation and see also the problems within that. Next, I will quickly review with regard to paging technique, which is a very important technique, please. So therefore, again, I advise everybody to please refer the notes, refer the textbook, and see the discussion which I made in the class with regard to paging. So what is going to happen in paging? In paging, the logical address space, suppose if I say this is my logical address space, this will be divided into equal size units, which are called pages, which are sequentially numbered from 0. So this is page 0, page 1, page 2, 3, and so on. And if you remember, I said that the physical address space will be divided into, okay, physical address space will be divided into equal size units called frames. So these are called frames. All right. So let me write, these are called frames. So frames are given number like this, we call frame 0, frame 1, frame 2, frame 3, and so on. Each frame can hold one page. Hope you remember this discussion. Any page, any of these page can be kept in any of the frame. Maybe I store P0 here, P5 here, P10 here. Frame size is always same as page size. Say for example, if this page size is 1 KB, this frame size will also be 1 KB. So that one frame, this is P10. So one frame can hold one page. Then after that, how is the address translation done? If you remember and recollect, I said the address translation is done by means of a page table. Okay, every program, every process will have a page table. So what will this page table contain? The page table will contain entries. These are called page table entries. So how many entries are we going to have? The number of entries in page table will be always equal to number of frames. Number of pages, sorry. Number of entries in page table is always equal to number of pages. So that means if my logical address space has got some 10 pages, if there are 10 pages here, then the page table will also have 10 entries, 0 to 9. Okay, if there are 10 pages, so these, what are these? These are page number entries, page entries. So how is the address translation done? That I will show in the form of a diagram so that you can be in a position to understand. Okay, so here the page conversion, page translation diagram. This CPU, some program runs on CPU, it will generate the logical address, also called virtual address. So this will be divided into two parts, page number and offset. Remember, I have shown this diagram in the class. You can refer it again for clarification, for further understanding. This is what? This is page table. So program running on CPU will generate logical address having page number and offset. One for every page, I said I will have an entry in page table. This is entry for page number P. Okay, this is entry for page number P. So what are we going to do? We are going to take this page number and index here. This will contain the frame number in which the page is present. Okay, so we take out the frame number, append the offset D. Okay, this is what is called physical address. So using this physical address, we access physical address space. So this is called simple paging technique. This is what the discussion that we had till the last class, I would say. Okay, the last class that we had. So in regard to that, I will solve a simple problem so that this problem also I discussed in the class, if you remember and recollect, so that you can be in a position to work out. Like for example, one case, logical address space, imagine, is 8 KB, and let us say physical address space is 4 KB. If I select some page size, I'm writing in short, page size is 1 KB. Okay, then how many pages will I get? How many pages are we going to get? So if I say number of pages, n is number of pages, is equal to nothing but 8 KB divided into pages of size 1 KB. So how many pages? So therefore the formula will be logical address space divided by page size. What is it? 8 KB divided by 1 KB is equal to 8. I will have 8 pages. How many frames will I have? Number of frames, let us say number of frames. Physical address space is 4 KB divided into frames of size. Page size will also be same as frame size. Both will be same. So 1 KB. So 4 KB divided by 1 KB. How much? 4. So therefore, physical address space divided by page size is equal to 4 KB divided by 1 KB is equal to 4 frames. So I will have 4 frames. See that diagram? So I hope you will be able to recollect. These are frames. So like that, for our given problem, number of frames are 4. Okay. So to refer one of the 8 pages, I need how many bits of address? That is called page number. 3 bits. 2 power 3 is equal to 8. So 3 bits are needed. 3 bits can refer 8 pages. 8 pages can be referred with 3 bits. How many bits of frame number F? 4 frames are there. So how many bits are needed? 2 bits. So 3 bits and 2 bits. So this is how we get the page number and the frame number. Now the next aspect is how are we going to get the logical address and physical address format. So now page size, again I'm writing page size is nothing but 1 KB. So to refer 1 byte, that is called page offset D. I discussed this in the class. Page offset is 10 bits. 2 power 10 is 1K, or the 1K can be referred with 10 bits. So 10 bits. So the logical address or virtual address will have a format having page number and offset. So look at that. Page number for our problem is how many bits? 3 bits. Offset is how many bits? 10 bits. So 3 plus 10 become 13 bits. So what is logical address space for our given problem? Let's check here. The logical address space for the given problem, just a second, let me roll it down. Okay. So look at this. Logical address space is 8 KB. 8 KB can be referred with how many bits of address? 13 bit. Is it not? Logical address space is 8 KB. So kilo need 10 bits. 8 need 3 bits. So therefore 10 plus 3 it become how much? 13 bits. 13 bits. So that is what I have got from the logical address format. And then coming to the physical address format, let us see physical address. Physical address will have two parts, frame number and offset. Frame number is how many bits? Remember here? Okay. Frame number, are you able to see 2 bits? Okay. So 2 bits. Page offset we said 10 bits. So 2 plus 10 become how much? 12 bits. That's right. And what is the size of physical address space in our problem? 4 KB. With 12 bits can't we access 4 KB, or 4 KB need 12 bits. So this is how the address is organized. This is how the problem is solved. So by means of this problem, this can be a simple 5-mark question for your exam. Okay. So you may be given logical address space, you may be given physical address space. Okay. And you may be asked how many pages I have, how many frames I have, what is the format, what is the logical address format, what is the physical address format, how many pages are there, how many frames are there, what is page number, what is frame number. This is a very simple example I want everybody to understand. So perhaps till this time was the lecture that we had in the class. So this is the point where we have stopped in the last class. I am supposed to continue from this point in the next topic. So the actual topic which we are supposed to start, all right, which we are supposed to start in the next session perhaps, is the philosophy of a very important concept called virtual memory. This is an extension technique of paging, an extension to paging, virtual memory. So this topic we were supposed to start in both the sections. So virtual memory is also very important because this is a technique which is used in most of the desktop operating systems like Windows, like Linux, and so on. So therefore, in the next lecture, I am going to give an introduction to what is virtual. It's a very important topic. You can say star topic. You can expect a lot of problems, lot of questions in the exam from virtual memory. So in the next session, I am going to discuss the implementation of virtual memory, the performance of virtual memory. So this was only a review with regard to whatever we discussed in the earlier classes of the chapter memory management. I sincerely advise everybody to please refer the notes, refer the textbook, and then prepare your own notes. Try to memorize this before watching my next video. Okay, right.